scientific and mathematics education. So there you go.
Well, just if he's smart, you pretend he's smart. So, and my last name is Gorbachev, so it's very hard to hide at the same time. But, it's not my accent and my last name, and people most of the time ask whether I'm relative or not. So
he's the grandson. Not really.
I don't have the spot in here, so it's really hard to justify. But thanks for the introduction, and really a pleasure to be here with Carl today and tell you about the story of building AI solution for the predictive maintenance with Carl. Carl is, I just realized you also 12 years at Teck, right? So we celebrate our anniversaries at the same year, actually. So Carl also has quite a background, twice as much in IT than I was. Graduate of MIT, worked at Berkeley Lab, and based in Washington, DC. It was called something else at the time, right?
National Bureau of Study.
Here we go. And I think also was at the Canada's National Research Council, did the research there, and in commercial space, I think started with IBM, was before ages there, and then through TELUS and into the mining sector as well. So I was a veteran in IT and artificial intelligence.
So I'm old, and this is improv. So the topic.
He calls me young.
It's all relative. This is about big trucks and big data and machine learning for maintenance. I'm with Teck Resources, and Teck Resources is Canada's largest diversified mining and resource company. We're the #1 producer of steel-making coal in North America, the #2 seaborne exporter of steel-making coal globally. We're the #3 zinc miner in the world. We're amongst the top 10 copper mines in the Americas. We're very much into the energy business at this point in time. And with all of that mining, we're also known as the leaders in sustainability in that sector and committed to responsible development. That's very much in one of our core values. And also in our core values is safety. We make sure that everyone goes home safe and healthy every day. And we usually begin a presentation like this with a safety message. Mine is that there are 2 exits in this room should anything untoward happen. And something good. So please head to those exits when you should anything happen. Right? Should you hear the fire alarm?
Yeah, they're taking safety really seriously. When I visited the office at Sparwood, then I saw on the fridge they had stickers like cautious how not to be eaten by a bear. So they're taking it seriously on many levels. I work at Pythian. I'm head of enterprise data science. I've been with Pythian for 12 years, did many different things and roles. Been the CTO for a number of years, run a team of DBAs. But Pythian is a company that's more than 20 years old, and we focus on helping our clients to win with the disruptive data and cloud technologies. We are one of the top Google partners. We've worked with Google for many years, and our partnership is very successful. We have 4 specializations, Google Cloud specializations, which is not many companies in the world can have it. And we're very global, actually. I lived in Canada for a while and moved to São Paulo in Brazil these days. And we have people all over the world. So stop by our booth to say hi. We have quite a few folks in here.
So the problem that we were actually faced with at Teck was really these trucks, and you can see sort of the size of the person on that truck, and that's a pretty small truck. That's a 930E. We have actually 400-ton trucks that will barely fit in this room, but obviously they go over very rough terrain. They get exposed to incredible conditions, both in the rain and the snow, and there are very many causes of failure, as we'll show you. We actually measure about 500 data points every half a second on every truck. That gives us about 2 gigabytes a truck per day, and that's an awful lot of data that gets accumulated. So we have fairly years of data. One of the things that Teck did or started 10 years ago, and it's unique in the mining industry. We actually built our own dispatch system, which is now called Wenco. And that dispatch system not only does dispatch, but it also does a lot of sensor and data collection. And all of our mines have the same system. Very, very unusual. All of our mines have the same system across our 13 mines, and we built our own Wi-Fi network also across all of these mines. We have more than 500 hectares under Wi-Fi. But a failure can cost in the hundreds of thousands, typically not 100,000, but really more in the $250,000 range to the $500,000 range, or the $5 million range, in fact. On suspensions, it can be extremely expensive. So we do have a lot of data, and because they're unpredictable, can a machine see what our people can see in the data? The approach was that there were 4 potential unpredictable failure types that were identified. Pythian was very much part of sort of identifying some of the classes that were reasonable, but also we wanted to identify a class that people were not good at detecting, and that would be actually a pretty expensive fix. We collected data around the potential cases. We worked with Pythian to determine if any of the cases were viable, to build a prototype, and we developed a production system with Pythian and provided a platform for future failure types. The most important thing I want to stress in this case is that we developed a production system. There are lots of mining companies who are, sandboxing systems, who have done explorations, who have done pilots. One of the things that I stressed with Alex and the Pythian group was, in fact, I am so uninterested in playing in a sandbox. We do it every day. It's just not one of the things that I want to see. I want to see a production system that gives us value in a short time. And in that phase 1 and phase 2 and phase 3, you see we did it sort of more or less within 9 months. We had a pretty good system running, and the production system took another quarter to put out there.
It's also interesting, I want to add that the way that we structured this engagement, that we try to approach is that when you're working with machine learning, you're working in a space full of uncertainties and unknowns, right? So we try to approach it in such a way that we move ahead in a kind of small stages iterations, when you remove as much uncertainty as possible to go to the next step. That's why we kind of try to structure it in those certain phases when we gain certain knowledge, so the tech is comfortable to make the next investments. Because of course it's investment of their resources and time and money spent.
It was very much a team approach on the tech side. It was our digital systems group, as well as the actual maintenance team or the production team on site. And in fact, one of the things that we did was we made sure that the production team owned the project. They own the value. IT will never own the value because the production team was actually going to use it and play. So there was a batch of data that was transferred to Google Cloud. When I say that, it makes it sound like, oh yeah, one day we decided to just upload all the data, and then we actually sort of applied this model, and Pythian was sort of from San Francisco was doing all the work. And the unfortunate part is that extracting large history of data from legacy comprised about 70% of the cost and time to make it go up into the cloud. 70%. And we actually had pretty clean data. It wasn't terribly bad, but pretty clean. And BigQuery imported the data in 20 minutes in the end. Some of our data imports in the beginning were on the order of days. So, thanks to Pythian, I think much of that data structuring, and they actually brought some tools to the table to help do that.
Yeah, we were fortunate that we had also Google Cloud platform at our disposal, right? There's a bunch of tools and products exist, from data prep to data flow, very easy and scalable to work with storage technologies like BigQuery. So it makes our job increasingly easier compared to we working with systems on-prem and so on. So of course, relying on library of automation, data cleaning tools, it makes it even easier. So that's kind of one-time initial effort. We try to minimize it because, again, we try to invest as little as possible at every stage to move ahead and get something right, to save us time and money. So any kind of automation by the platform, by the tools is very welcome.
I think the other piece of the data modeling was, at first Pythian did almost everything off-prem. So we have mines, they're in areas that are, well, the elk roam freely, the mountain sheep actually graze on our pits. bears walking around. So it's a very different environment that data scientists don't often get to visit. And however, I think it was crucial that actually the Pythian team really experienced all of the data issues on site, and so that they can understand what the data actually meant. I'm having trouble with my ear. There you go.
Traveled in there a few times to actually meet the team and work together, collaborate with. That was quite a revealing experience.
That's all right. I'm still going to try this one, so we'll put it over here. But you'll see some of the volumes of the data that were analyzed to actually create the system, and keeps on analyzing, in real time. And we do still have a problem with uploading the data in these kinds of volumes. So, but I think I really wanted to stress that them coming on site made all the difference. So once their data scientists were on site for a couple of weeks, that's when I think most of the breakthroughs occurred. So high voltage failures. What happens is that we have a pretty intense high voltage system on the truck. It can actually cause a fire on the truck. The truck actually explodes or catches fire. Has an $8 million loss. So they're actually more expensive than most Maseratis. We do have a problem in that with these electrical failures, they're hard to find. And basically, you can get up to a $5 million payback on these annually if you can find them all correctly and diagnose them predictively before the fault happens. If successful, we can apply the frequency of alarm analysis elsewhere as well. So we have about 42 of these kinds of problems, not only with the electrical system, but with many systems on the truck. And so it was really a matter of pattern recognition of this and prevention of cascading failures, because once one of the failures occurs, then of course other electrical failures may occur.
Yeah, and one of the interesting things that I also learned is that it's not only direct cost of repair or potential direct cost of the truck that experienced during those unexpected, catastrophic failures, but it's also that in many industries, the revenue of the company is directly proportional to the uptime of the whole truck. If the whole truck works, then you get coal and you get money. If it doesn't work, you don't. It's as simple as that. So in a resource-constrained environment, which is most of the time on the mining sites, then it's basically directly proportional to revenue. So it was quite revealing.
So we did have some alarms by unit, and the sort of the alarm profile is everything's fine, everything's fine, everything's fine. Then you get these alarms coming in, and then you get this kind of alarm coming in, and then you may have machine learning actually predicting one of those high-level faults, and or a high-priority event. And I think that at this point, perhaps Alex, you can begin to sort of really describe some of the things that you saw.
Yeah, the challenges were that their asset health supervisor had like a big screen with lots of alarms running, and there was so many of them. They they spotted some and maybe had their own way of how to detect and predict the failures. But most of the time there's a little hope for a human being to try to interpret that. So that's why it was a push for machine learning, why the Teck was so keen to invest into this.
So you see here different profiles for different trucks. There are 3 shown there, and one of them actually actually demonstrated an alarm condition that resulted in it coming into the shop and actually being diagnosed with failure.
In the model training, what we also learned is that we've learned that while training the model, how do we optimize the threshold in terms of optimizing between false positives, false negatives, right? Because if the cost of the failure, unpredicted or uncaused failure, is so high, it may be okay to check on the systems a few times extra, even if there's no failure going to be found, right? So based on this, we were able to tune the model in such a way that it could have some false positives, meaning model predicts failure and actually wouldn't be one, but try and never miss an opportunity. And from the 3 months or 3 to 4 months, from what I remember, the statistics is there was 6 failures predicted. 1 was missed by the model, and 4 of them was actioned that one, and I think 2 the staff decided not to action for whatever reason, which is interesting because it not only brings us to the point of you optimize the thresholds in the model by the numbers, you have to take into account the human threshold. We actually tweaked the thresholds to be not optimal by the numbers, right? but to be less alarming, because we were afraid that people would not believe the AI giving recommendations when there are actually no failures, right? So we intentionally did that in such a way that AIs could miss maybe a failure, but initially wanted a human to trust it. So that was kind of a trade-off between, perceptive-based and a human-based factor, and what system and financial numbers basically telling us. This is our plan of attack, how we normally attack problems after we do initial discovery. We usually start from a very simple model, type of linear regressions, and then go random forest and boosted trees. And during regressions, as much as they beat up, they're really useful because you can, interpret them, you can get an inference with them, and sometimes they work really well. And then go down to a more complex one, like a neural net, convolutional networks, recurrent neural networks, and so on. And we had a certain plan how we would do feature engineering and so on. This was our plan of attack. Of course, the reality was a little bit different as we were discovering it, but that's why we moving ahead in that iterative approach. What I wanted to talk to you about, because this is a very, I think, useful piece. It goes a little bit into technical detail, but I think you'll like it, is how do we take time series data and set of events, instead of certain knowledge about past failures, and turn it into the data model, turn it into the machine learning data set. Like, if you work in data science, and if you even participate in things like Kaggle, you got nice, cool data set that somebody prepared for you, and bang, you get a table with columns and features and things. You don't get these things in real life. You spend a long time with a subject matter expert to try to figure out how to turn the time series of sensors and alerts, stated and stateful alerts, and turn it into some kind of feature model. So what we've done is that we look at the past history, and here you can see that each line is kind of let's say, a whole track. And then some of them experienced a failure, or some of them were undertaken maintenance that would otherwise lead to a failure, right? So we look at those, analyzing those, and work with the domain experts at Teck in order to basically, based on that, mark certain periods of time before that as the danger zone, right? This is the place where the failure is pending. So we expect, our hypothesis is that if we look at the statistics during this time and the patterns of over the just sort of immediate prior to that, we should be able to see a certain pattern that would be indicative of a failure, right? So then we also thought, okay, what periods of time for each track would be clean, would be safe, and we should not expect any indications of failures. And it's not that easy, because sometimes the past history may miss some of the events. Sometimes they were uncertain. So as a result, we ended up with a system that allows us to basically, for each of 108 tracks on the 3 mining sites, mark a period of time in the history when we are quite certain that the track didn't exhibit any behavior, pending failure behavior, and the ones that were when we were uncertain. What we've done after that, we basically took a sample, took an observation from those green and red periods when we knew, or we thought we knew, we think we knew based on our interpretation, that the certain pattern should be present. And that's how we got our observations from machine learning. So you can see in that example, basically each tick in here is basically, an hour or over a day is a point in time at which time we simulate taking the snapshot of what we know happened before that and feed it into the model. And how do we know what happened before that? Well, there was different ways we can turn the prior events, time series data into features. And we basically used a reasonably simple method of actually applying various aggregations to alerts and sensors for other models in order to create like a pattern, give model the pattern over time. For example, give the daily average of alert counts for the last 4 days plus an average for the time ahead as a comparative. So giving the machine some ability to find patterns in those. And we experimented with those, with its counts, with it, standard deviations, unit, and so on. And we worked with the subject matter experts, because what happened is that we only had like a 42 or so failure over 3 years. Some of them were at the time when for some reason there was no data at all coming from the trucks, because it was the sensors were down or something. But so we profiled those, and we ended up with the 30-something failures. 30 failures is very little for machine learning to train on. It's a huge opportunity to overtrain your model, right? So as a result, what we've done is that for each failure, we actually expanded our learning range a little bit, because we went for a number of days before. before the failure happened, right? So we can have much more samples of those, right? So it's a bit of a cheating because our data points became dependent on each other a little bit because we go in past and take a history from quite a longer range before. But it worked quite well and allows us to extend our training set to like several thousand of those, rather than picking them out of those ranges. Now, even a few thousand is not enough to build a very complex model because we had to work with thousands of alerts and events. So we worked with the subject matter experts in order actually to narrow down which ones are definitely irrelevant and left only the ones that may have some predictive power for us. And we also had to stop at quite simple models. We basically ended up with random forest models working best for us because we go down to more complex models like neural networks, which we did. It significantly overtrains the model, so it doesn't generalize well. And then in cases when we have significantly more failures, just more complex models are definitely feasible.
And we also push them for speed. So let's get this thing done. Let's get it into production. Let's see what happens.
Yeah. I remember it was in beginning February, and Carl on a conference say, I don't want to do like any improvements anymore. I think we're good enough here. Let's press in production. I have 6 weeks, 6 weeks to get it done. I think we were late by 1 day instead of Friday. 2 days right on Tuesday in production. But it was a quite a push. Now the decision to go to production, because the value was in the hands of users, the users need to be comfortable with that. And there's always resistance to change, right? So, and we were presenting them the confusion matrix, the recall, the accuracy, all kind of metrics, and told them how good it is, and but it was very hard for them to kind of believe us that that's a good metrics to use. So what we in the end ended up doing, we actually extended our proof of concept a little longer in order to invest into this. We actually started simulating. What if we apply our model on the test data, on the unseen data ranges and trucks by the model? How it would look like? And then we try to represent them in time, for example. This is a good example of how we present it in the time series. This is a truck as it was working. This is where the failure happens. This is what our model would do on that data, right? So it gives them an idea. Okay, so it's over time. It goes and goes, and we done it for a number of the samples, and then it kind of gave them a feeling of comfort that okay, this kind of work, right? But when you talk to them about recall, accuracy, precision, F1 scores and whatnot, it doesn't kind of give way, right? So you have to present them and the user that just give way. So here's our architecture. I don't know if you want to mention anything here.
So, again, on the architecture, like I said, 70% was data, but the other 15% was putting it into production. So how do you actually flow all this data in real time into a machine learning model in the Google environment? And what kind of components do you need in the Google environment? And how do you make that all work with the data sets that we have? And so you'll see in that top square there, that's basically our Wi-Fi system that dumps data into the Google Cloud Storage, an Wi-Fi system, as it says, cloud storage, and then from that point on, it flows into a number of different areas. One being the API systems that Google has for logging, and that goes into Stackdriver. And then the other part really goes into the compute engine and BigQuery, and then Bigtable, and from there it actually logs back or flows back into the predictive API endpoint. And I don't know if you have any other comments on the architecture.
Right, there is of course, it's kind of quite simplified. There are quite a few pieces, of course, underneath, and there's a whole exploration and training environment that fit into that actually, in the end, dumps the model into the model repository, the cloud storage as well, of course.
Yes, that was Pythian's big, I think, contribution in that.
Right.
Yeah.
But the cool thing is that our Google Cloud platform has all the tools required to build, completely automatically running production system that basically runs and monitors itself and raises alerts when needed, right? And one other thing I wanted to emphasize is how we approach the integration with the on-prem systems. What we've done is that we actually, in the end, developed the API, the REST API, which can then be called from on-premise on demand to get a prediction. And if the alarms are if the warnings and critical conditions are raised, they would be put into that system and would be visible to end users, right? So we built something new, but we integrated it transparently into the call into the old quote-unquote system that users use when they expect to see this thing. So we put them in front of their eyes through this kind of API style integration.
So we're running out of time here, so what we'll do is we'll quickly go over this one. You've seen a little bit of a graph before on this, but basically 2,200 inputs were looked at. We're looking at this year much more than 1 million, more like $2 million savings, and we realized 500,000 in the first quarter of the year, just from 6 trucks. So, yeah,
this is a cool slide. Maybe you could talk a little bit around this.
So one of the things that happened, of course, was the truck was brought in. It was actually alerted to have a problem. The repair was attempted. The failure probability that the machine learning algorithm was predicting didn't drop. And so the truck was out there, and the machine learning algorithm was going, this truck is going to fail, this truck is going to fail. It was re-inspected, and cracking was found in some of the components, which would have actually led to a fire, because it was a high voltage leak. And so it really saved a significant failure, but it really increased the trust by the maintenance folks in this system. They couldn't find it, and the machine learning said twice that this is going to be an issue. So that was actually a big catch. So
exciting to see those.
And the human learning very quickly, they were skeptical, but the folks in maintenance, the young folks in maintenance, were not. They really wanted to build it. They really wanted to see it happen. They owned it. But one of the things that we discovered with Pythian was that, we wanted to make this brand new interface that people could use with joy on the field, to this red light, yellow light, green light kind of interface, and everybody would be happy. And the thing was and then we sort of said, not a chance, not a chance. And the maintenance guys were really sort of kind of looking at us funny in terms of this red light, green light thing. And so we built the ugliest interface, or we added to the ugliest interface in the universe that, just a line saying, this is from the machine learning system, but it's just another alert. Because they're used to looking at this. This is what this guy does all day. He looks at these alarms at the end of the day and he goes, well, this one's, you've got to pull this truck and not this one. And that's what worked. Just keeping it incredibly simple on the interface part. Very, very, very silly, very ugly, but again, it was actionable and it worked. So we have a lot of potential use cases, over 64, that we could actually increase the scope and look at more breadth as well, and also across many more mines and many more trucks. We have over 400 trucks. Right now we're saving approximately, call it $5 million on 6 trucks. So across 400 trucks, you can obviously do the math. It would be almost $1 billion. And so on the basis of this, we sent 5 people to Google onto their ASL training for 5 weeks. For a mining company to do that is almost unheard of. And so that now we're far better able to do some of this work in-house. I think on the data side, we're still going to rely on Pythian for their assistance. But the Google Machine Advanced Solutions Lab has really changed our company's future. We're doing a number of projects now with them, with our own team.
And it's much easier for Pythian to work with Teck when there's a certain background knowledge already. So we like our collaboration is faster and faster.
Yeah.
So this project is a good investment.
So thank you.
Thank you.